All right, everybody, welcome back. So we're operating on normal time, not on GFDL time, I assume. Um, so as everybody's getting like settled, if you want to pull up that GitHub repository and download its content, that would let you like follow the presentation with me, with the notebooks. Um, I've already run the notebooks because I don't want to be like, waiting for like a minute for like a, Python cell to execute. But you guys are listening, so you can run your Python while I'm talking and while you're listening to me, hopefully. Um, so if you go to that, to my GitHub, you go to the repository, and the newest one that I just finished like yesterday is gonna be the one you need to clone. And with it, I have like that text file, that conda env MOM6, and that you can use to create a conda environment, all the instructions on the README. And so if you follow those 4 lines, you can get the conda environment up and running. And with that conda environment, you can start following the notebooks with me. So we'll start with the Philips 2 layers, and then we'll do like a CM4 examples. Like I said earlier, if you didn't manage to get the data for the Philips model to run, there's a little like fail safe. I copied like the files that we're gonna need into that directory, data Philips. And I'm gonna try to run you through like a few exercises, and obviously there are solutions to the exercises that I put into the solution. So I would recommend that you use the one without the solution to the exercises, so that to make it more interactive and a little bit more fun, hopefully. But if you're like, if we don't have time to finish everything, the solutions are gonna be there. So the first thing I'm gonna do is basically load the data from the experiment that hopefully you were able to run. So I ran it, and so that's where my data lives. So I'm gonna use that the prognostic variables that were written there, and I'm gonna add the grid metrics, and those are typically written in that ocean geometry file that MOM6 is writing. And just for consistency, I'm gonna be renaming like a few variables, so that when I merge the two data sets together, it does it like smoothly. So in the ocean geometry, it writes as long h, light h, long q, lat q, and I'm gonna write them as xh, xq, yhyq, which is like the same thing that's written in prog.nc. So it's just a matter of like reconciling all the different names. So when I do that, I obtain my X-array data set. And so what we're gonna see here is that we have like a bunch of like different coordinates. We have the xh, yh coordinates that relate to the cell centers, and the yq, xq that relate to the cell corners. And different variables that can be defined on different points. So basically with like a different set of coordinates. And as we're gonna see, like the H or U and V are gonna define on like slightly different set of coordinates. And that's what we're gonna need to work with. And I'm gonna show you how to work with those different type of coordinates. So one thing we can do just to get started is look at our initial condition and see, okay, what did we do with that model? How was that model initialized? So MOM writes those initial condition on demand if you want it, and gonna write it in that MOM6 netcdf file, which is actually very useful if you want to make sure that your model is starting the way you think it started. So again, here a little bit of like renaming because of different naming conventions. So I'm gonna make it like all homogeneous in that case. And to make it like a little bit like easier to visualize, I'm just gonna compute like a zonal mean of my, so that's gonna be my zonal velocity. And I'm gonna plot that onto like a layer slash latitude plot. And so for that, I mean, Xarray does it like in a way that's very easy, where I can basically average over like a set of dimensions. So I don't need to know in my array how my array is formed in terms of like, okay, which dimension comes before the other. And it's all like set by labels. And so if I pass, in that case, those like XH and, XH and XQ dimension, it's gonna know exactly how to average my arrays. I'm gonna squeeze the time dimension out of it because it's only one time record, so I don't need to keep that extra dimension. And so I'm gonna do same type of thing for the latitude. This doesn't matter too much. It's just a way of like making the latitude like a 2D array, so I can plot against it using my my p-color mesh. And so that's what we're getting. So that was our initial condition from the simulation that that Alistair ran this morning. So you can see those perturbations in velocities, and so that gives us like a first idea of like, okay, this is what we started with. So speaking of axis, that's where we're gonna come into something like actually pretty interesting. So Xarray has all those dimensions, like the X on the H point, Y on the H point, X on the Q point, Y on the Q point. But for it, it's just like a list of dimensions. It doesn't know what are like the relationship between those dimensions. We know that we're working on a staggered grid, and we know that basically every H point is gonna be in between two Q points. But Xarray doesn't have a way of knowing that by construction. And so that's where xgcm basically filled that void of like basically creating like some knowledge for Xarray as to what axes are gonna be like intertwined with what other axis. And so again, reminder, so MOM6 is a supergrid model. I think you all should be familiar with that, but just as a quick like reminder, we're gonna have the tracer. The tracer is gonna be at the center of the cell. You're gonna have like the vorticity and Coriolis that are gonna be on the corners, and U and V on each face. So east, west, and north, south. And so because of that, then we're gonna be defining like different metrics for like your dx, dy. All your dx, dy are gonna be dependent on which point we are talking about. So in that case, okay, let's define basically like a xgcm grid. So the xgcm grid basically is gonna allow us to define how are the different axes related to each other. And in that case, I get 3 axes. I've got X, Y, Z, and I'm gonna define my tracer point, so XH, to be at the center, and my in that case, vorticity point to be outer, meaning on each side of my centers. And this is going to be dependent on whether or not your grid is symmetric or non-symmetric. But in that case, we're working with like symmetric grid. So outer is the one that works for me. And I can also pass the fact that it's periodic along the X direction. And similarly for like other axes. So now, okay, let's do a simple example. And let's say I want to compute the speed. So basically my U square plus V square. Because U and V are not located on the same point, then I need to do like an operation to bring it onto a common point for which I'm going to be able to put it to the square and sum it up. And so one way you could do that is say like, okay, let's bring everything to the tracer point. So I'm going to take my two zonal velocities that are like, remember on those faces, and I'm going to say, okay, I'm going to interpolate it along the x-axis, and that's going to bring it to the tracer point. And similarly, my meridional velocity, I'm going to bring them back to the tracer point also with like that operation, that's interpolation. And so that's an xGCM operation that's basically going to take like those two quantities and it's going to bring them onto the points where they belong. So they're going to bring it onto the x, h, y, h. Do you see my mouse? Yeah, you see my mouse. So it's going to bring it onto the proper point without you having to say anything. xGCM knows those relationships between the different staggered point, and it's going to put it on the correct point. So if I were to plot the thing, that's what I would get. So again, pretty straightforward way of computing your speed. And now we can do like a quick exercise for those who are like up and running. So say, what would you do if you wanted to do the same operation, but instead of having it on the tracer point, you want it like on the vorticity point. So, all right, sorry, that was 1 minute. All right, so what did I do there? Well, I just did basically the same thing, but instead of interpolated around like U along X, I interpolate along Y and vice versa. And you get actually something like very similar, because obviously everything's like very, I mean, the H point and the Q point on that grid are like pretty close to each other. So you're not going to be able to notice just by visual inspection. But that's like, okay, that's just the speed. We can do stuff that are actually a little bit more exciting. We can look at like relative vorticity. Relative vorticity, we're gonna do basically similar construct, except that instead of like taking the half sum with the interp function, we're gonna differentiate. So we're gonna take the diff, and we're gonna divide by the proper metric. Add your dv dx minus du dy with again the proper metric, and that's what you get. So on the left, that's what we computed with like xGCM, and as a matter of fact, we also have like the relative vorticity saved by the model, so we can make a direct comparison, and it looks pretty good. Now, if you make a difference of the two, you're gonna start finding like some slight differences, because the model saved its vorticity at all time steps and everything. So there's a little bit of of a mismatch. You don't get like bitwise reproducibility, but we get something that's just for the purpose of demonstration, kind of like good enough. All right, so again, I think I'm gonna skip on most of the exercises because of the time constraint, but I really recommend that you guys try that at home. I mean, we can do also like the potential vorticity, and that's a pretty easy one to do as well. And so I'm gonna skip over the details, but you should get something that's also like very similar to what the model is giving you. Then time series. Pretty straightforward. Again, with X-array, we can take like the relative vorticity, multiply it by itself, multiply it by the surface of the cell. So in that case, the vorticity is on the corner point or the vorticity point. So you have to multiply it by the proper area. So in that case, it's labeled AQ for like area on the Q point. You sum over the horizontal dimensions, and you can get that time series for the different layers of the model. So again, X-array and xGCM make it like pretty straightforward for you to build a diagnostics and execute it in a very very few lines of code and get to the science, which is the important thing. Again, we could do an exercise and do it also for like the potential vorticity, and in that case, make an anomaly to the initial condition because the two are like quite different, and you would get something that looks like this. All right, so now let's shift gear a little bit because I think that's what, like 20 minutes left. All right, so now I want to touch also on some like more like realistic configurations, and again, that's part of like the same repo, so you can switch just to the CM4 example notebook. In that case, what we're gonna do is we're gonna be like loading data directly from the ESGF node. So apologize if it takes a long time for the thing to load. This is like this is not something we have too much control on. So hopefully that's gonna be working for everybody. And I'm trying to run through the clock to let you guys run that cell. All right. So basically what you should get is something that looks like a 20-year average of like temperature, 3D temperature, and cell volumes. Obviously, we're not going to work on all that data because that's going to be a little bit too expensive to manipulate. So what I'm going to do is I'm just going to take like the first months, and so I'm just going to grab the first time record to save some space, and again, to try to save time and make sure that it doesn't do things, it doesn't try to reload the data every time. I'm just gonna load it once and for all into memory. And then every time I run a plot, it's not gonna try to pull the data out of the ESGF node every time I do that. So I want to talk a little bit about plotting, and one of the common mistake that's made, and everybody does it when you start like looking at GFDL models, is to use the 1-dimensional X and Y coordinates as the coordinates for your plot. And those coordinates are there for like historical reasons, but they are not the true geographical coordinate. I cannot like put that, like say that like loud enough. You should not be using that. And the way you can spot that you get the wrong coordinate is that if you see like like Canada or Siberia going like all the way up onto like the, the top of your plot, you got it wrong. Everything else, I mean, looks pretty okay, but it's still not the right coordinate. So you should not be using that. And the right way of doing it is to use the two-dimensional longitude, latitude. They're often named geolong, geolat. Naming convention can vary in that case. The data that's been processed for SEMIP refer to them as like LON and LAT. Make sure that you use the one that are like two-dimensional when you're using like the native output from OM4, CM4. And when you do that, then you start to see like the Arctic Ocean looks way better than when you're using the wrong set of coordinates. So that's using like matplotlib, and you're gonna say like, yeah, well, yeah, your plot are okay, but I'm not gonna put that in a paper. That doesn't look quite good. And that's why I recommend that you look into Cartopy, and Cartopy has a set of like many map projection. So you can pick the one that you like better, that suits better your analysis. And again, I don't want to go too much into like the different details, but I want you guys to have that as a reference. So those notebooks, if one day you're like, oh, how do you do that in Cartopy again? Well, it's in the notebook, and this is typically how you would make like a map. That looks to me like something that I would be okay putting in a paper. Again, you can change the projection. Sorry, that won't get a little, let me see if I can just make it smaller. Okay. All right, so that looks like a pretty decent polar stereographic projection. So sorry. I was gonna say as an exercise, again, I don't think we're gonna have time right now, but try to do the same and take like a Miller projection, take the temperature at 1,000 meters, and actually you're gonna get something that should look like that. And now I want to talk a bit about data reduction. So again, data reduction, one important thing to remember is that we're writing a lot of variables like vol celo, area celo, or THK celo, which represent the volume, area, and thickness of the cell. Those are the proper metrics that you need to use if you're doing some data reduction. For various reasons, the model is like taking its topography and adjusting it in various ways. But the result of all those adjustments are gonna be taken into account into vol celo, area celo, THK celo. So that's the one that you need to be using. So I'm just showing a little bit what it looks like. It looks bigger, at the equator. Earth is a sphere, nothing like nothing new here. And one thing that I like to do personally is to just to make sure that I get my code right. I always try to make like, okay, let's compute like the mean ocean temperature. I know the result should be around like 4 degrees Celsius. So I write my code and I always do that little sanity check to make sure that this I'm getting right. And in that case, what I'm doing is I'm just taking my 3D temperature, multiply it by the volume of the cell, sum over all the spatial dimension, and then I renormalize by volume of the cell that I sum along all the spatial dimension. And I get something that's about the value that I expected. So I'm happy and I'm confident in my code. I could do the temperature profile. I'm gonna let you do that as an exercise. One thing I want to show you too, and that one I think is pretty cool. So John Crusting, sitting over here, has put together like a really cool package named Basin, and this is going to allow you to generate like Basin codes, and just showing you those Basin codes. So that's basically separating the world ocean into like different basins, and that would work for like any configuration that you're running, because it's not based on like a particular configuration like OM4 or CM4. It's generic functions that are going to adapt to whatever like domain, like say 1/8, 1/12 of a degree, 1/24, what have you. It's going to be working on that, and it's going to separate it in like different basins. In that case, what I want to do is I want to look at the temperature section across the Atlantic. And so I'm going to do that by basically selecting, so that's that where function. I'm going to select everything in my data set where that basin code equals to 2. So 2 is the Atlantic in that case. And I have a little bit of like work I need to do on the latitude. Again, the latitude, I'm gonna take all the latitudes in that area, and remember that because the grid is irregular, there's gonna be the increment is not gonna be exactly the same everywhere, and we're gonna see that actually in the next plot. So your latitude here is the red line, and so hopefully you can see it from there, but if not, that's what the black line is for. The increment in latitude is not quite the same everywhere. So again, don't plot it against that y coordinate that's in the data set, because there's no reason for it to be accurate. You want to plot it against the true 2D latitude that in this case we have reduced into a vector by using that zonal mean. And if I do that, this is what I get, and this looks pretty good if you compare to say some WOS section. This is typically what you expect. So again, that's kind of like an example of how you can actually pretty easily put together some really interesting diagnostics, leveraging like the different tools that we have in X-array, the CMIP basins, and all of that. Again, as an exercise at home, you should try to do it for like the Indo-Pacific. You got 5 minutes, right? Okay. So I wanna. Okay. Oof, okay. Okay, understanding the supergrid. So that's one's gonna be. Okay, that's important. Maybe that one you don't have to follow. You can do it. You can do it at home. But the idea is that this. So MOM6 is a C grid at all those staggered points. The supergrid is gonna be the union of all those points. So you're gonna get something that, say if your model is n by m, you're gonna have something that's 2n plus 1 by 2m plus 1 in the symmetric case. And basically you're able to infer all your points, all your tracer points, all your Q points from the supergrid. And that's, again, oops, that's how you would typically like recover those points. Say, for example, you lost like the longitude and latitude of your arrays. If you have the supergrid, you can always recover the staggered grid. And in that case, well, the tracers, if we're in the symmetric case, the tracers are going to start at index 1. Remember, in Python, 0 is the first index. So I'm going to go with 1, and I'm going to like bounce all over. Like I'm going to jump over the second one to number 3, number 5, and so on. And for the corners, you would just start on the edge, so at 0, and you would just like take every 2. Again, that's something you should look at home, make sure if you're a bit confused, just sit down with it and try to plot the thing. Again, as an exercise, I recommend you try to do it with like U and V points. And you should get something where you get your tracer here, that the red square, and the U and V are going to be green square and green circle. Okay. Just a quick note, and that's something that you guys will probably have to do quite a bit, is remapping. And in that case, it's not the remapping like online in the model that we're talking about. It's just like, okay, how do I take my output data and compare it to something that's on a different grid, like World Ocean Atlas? And that's where xESMF comes in very handy. And so xESMF allows you to basically remap your data on the sphere. Again, like never use grid data. I mean, there's like a bunch of like MATLAB or Python functions that are like designed to work in Cartesian space. These are not the tools that you want to use. You want to use something that's designed to operate like on a sphere. And xESMF is that kind of tool. There's a pretty good documentation on it. So again, I would refer you to the documentation. And so, like as a quick example, I can just like create like my grid object for xESMF, where I'm gonna take like the longitude, latitude of the H point and Q point. I'm gonna create a 1 degree grid where I'm gonna do the same. I'm gonna create like the center and the corners. And I'm gonna show you like 3 different methods. For the nearest neighbors and bilinear, you only need the tracer points. If you want to go conservative, then you need to be able to compute the areas of the cell. And in that case, that's why you need those corner information. And again, probably something that you guys are gonna have to do at home for the sake of time. But that's kind of what you get when you remap the thing on the 1 degree grid. And I can show you the different methods. I mean, you're never gonna know, like just like from visual inspection, which ones are which. But again, all those different like remapping algorithms have like different properties, and you need to figure out which one is relevant for you. And I think with that, I'm running out of time, and so I'm just gonna skip to my just like my final words. If you go in the notebook, I've got a really cool diagnostic with like the Gulf Stream North Wall, so you guys should look into that. And my final words are gonna be, there's a lot of stuff going on with Python and X-Array. I mean, it's a very, very alive community, and we are very much enjoying developing within that framework. So there's a lot of stuff going on. Look into like our GitHubs, and also a good starting point if you're new with MOM6 and you don't know where to start is to also look at that MOM6 analysis cookbook, where we try to put in like some very basics on how to get started with analyzing the model. And with that, I think I'm out of time. And again, I recommend you just like take the time to work through the notebooks and look at the exercises, and I hope you have fun with it. And that's it for me.